Okay, welcome to lecture 2. At the end of lecture 1, we finished off by finding the acoustic wave equation, deriving the acoustic wave equation, understanding all the assumptions that went into it. But you may have noticed that, this is in terms of pressure, the time derivative of pressure, spatial derivative of pressure, and the sound speed here. But originally, we talked about our sort of intuitive understanding of sound, that it could be fluctuations in pressure, it could be fluctuations in density, it could be fluctuations in particle velocity, and of course there's energy transported by sound waves. So what I want to do today is just do a shortish lecture on connecting all those things. So the idea here is simply that we're going to relate pressure to density, velocity, and energy. And so we'll begin with the second of the three equations we used to derive the acoustic wave equation. So we had conservation of mass, conservation of momentum, and an equation of state. So let's begin with Euler's equation, or conservation of momentum equation, and the unlinearized version of that. So this is a very fine-tipped pen. Okay. Yes. So Euler's equation. Does anyone remember it? That's what I would normally ask, but that's not going to happen. Not this year. Okay. Euler's equation. You probably remember it from, some courses on fluid dynamics. Of course, here we never get to the Navier-Stokes because we're taking the other branch and we're looking at, where compressibility matters and fluctuations about the mean. Okay. So we had the Euler's equation there. That's conservation of momentum. Better write that down. Just, this is something to hammer into your head and just remember it for all time. And then we linearized that. So the linearized version looked like rho naught. Of course, we talked about the mean, and then v prime, the perturbation, dv prime dt, and then minus the gradient of p. So where can we go from there? Well, here's a classic, just an absolutely classic move. Take the curl of both sides. Okay. And if you have taken a fluid dynamics course, you're thinking that's going to make you think of something. You can't help thinking about it. We're going to get there. So we take the curl of both sides. We get d by dt, curl of v prime, and then we have the curl of a gradient. Right away, you're salivating. You're practically freaking out because you recall from way back in the early days that the curl of the gradient of anything is equal to 0, right? Okay, so boom, big 0 there. We don't have to worry about this. Density anymore, and we just have this nice little expression here, right? Does this look familiar? It may look familiar. Another way to write this would be where omega bar is the vorticity, okay? And that's what I was alluding to there with some great memories. I'm sure you have great memories of looking at vorticity, okay? So vorticity is constant. And we can choose it to be 0. We'll put that in parentheses. Chosen to be 0 if we want it. Kind of inspirational. So yes, this would be called irrotational flow, the idea that the parcels of fluid that we're talking about vibrating, now those parcels of fluid don't have any rotation, so they're irrotational. Omega equals 0, okay? So for irrotational flow, in other words, omega equals 0, we can define a potential, okay? So I'm going to keep the primes. I'm going to keep the primes. So I'm going to say, okay, well, because the curl of any gradient is 0 and omega equals 0, so this term here, right, we have 0 there, we can define this because that would be true for any potential phi, okay? So I'm sure this is all very familiar now. So what is that potential? So let's see, what do we have now? Let's go to a new page if I can. No, I can't. I got to add some pages. Okay. I'm going to add just so many pages. Okay, now let's try to go to new page. Okay, wow, I did it. Amazing. Okay, so yeah, we have defined this potential, the gradient of phi, and is related to the velocities, and the phi is the potential. So what do we have now? Let's put it into our momentum equation. So now we have gradient of d phi dt equals minus the gradient of the pressure. So we can write T plus P equals C naught, and we'll define that C naught as 0. So just did a quick integration there. And we really have these two equations here that fall out. The definition of the potential, and then the pressure in terms of that potential, okay? So now what does the wave equation look like? If we sub that all in, okay, in terms of phi, I should say equation becomes, well, we have the Laplacian of phi minus 1 over c squared, and the second order time derivative is equal to 0. So obviously an identical form, okay? And you can see that from this equation, you can very easily see how pressure and particle velocity are related. So I'll just say Rp and B prime, and I think I've been carrying the primes through. I've been careful about the primes, yep. Okay. How are they related? Well, first of all, through our definition and through this nice little equation we had above. And, you know, I'd say those are highlight worthy, right? Oops. So this is, I think, a pretty intuitive little relationship between the pressure and the velocity. And of course, the important thing to remark here is that this is a scalar property, and this is a vector property. And so you can think, of course, if you're imagining the particles vibrating, they vibrate in a certain direction, but the pressure is a bulk thermodynamic property, which doesn't capture that you know, you need an ensemble of particles to exert a certain force on a certain area to get the pressure. So you don't really have that directional component. And actually, you may recall from lecture 1, we actually assumed that, you know, over our parcel it was uniform. Okay, so we'll go ahead another page, and we'll think about density. So we actually, in lecture 1, we said, okay, we're going to say there's some equation of state that says that density or we could say, say pressure is some function of density, for example. We linearized that, and that was very helpful to define what sound speed was. But in some cases, we can actually write down exactly what that equation is. Okay, so for instance, I'm sure you're all thinking, you just can't help it. You would yell it out if you were in class right now. You would say PV equals nRT. So for the ideal gas, which of course we need an adiabatic process, which of course save you the trip to Wikipedia. That's no heat lost or gained. So you have some gas where it's vibrating, but there's no heat that's lost or gained in that process. So, again, ideal. We have this PV equals nRT, or we can write that in another familiar form in terms of density, right? N over V is just density because N is the number of particles. And this is also called Boyle's law, right? I'm sure you've seen this. Boyle's law, ideal gas law. So a really explicit form of that assumed equation of state. So we can actually just, this is also linear, right? So we can actually just say, okay, what is the sound speed then? Well, C squared we had is dP d rho. So we get this gamma RT. R, of course, is the gas constant. And gamma is the ratio of specific heats. And typically that's constant as well. I'll just put that here. But again, topics for a thermodynamics course. And in air, you can come close to a nice solution for that. Doing some more sophisticated stuff. And you get something like C equals 0.6 T plus 331 meters a second. Okay, and you can also measure this empirically. So this agrees with the empirical results. Back in the old days when you could just go measure the speed of sound and that was a career, good times. So that's for a gas. So in liquids, what do we start with in liquids? Well, a good starting point is with the adiabatic bulk modulus. K sub S. And it's essentially defined as 1 over the compressibility. So I sort of pulled this out of nowhere, but you can think about our original expression where we have dP d rho, define a compressibility, and then define 1 over that. So it's not too much of a stretch. It's a pretty intuitive approach to this. So, okay, so what do we do with seawater? Well, basically the equation of state for seawater is this incredibly complex thing, and really is a topic of research, and so something that we'll look into on assignments. But generally, so it's many polynomial relationships which are derived from huge sets of data. Okay, so generally we have something like C is equal to C, P, T, and S. Okay, where we have, of course, the pressure. This, of course, is temperature. And this would be the salinity related to the density. These are all related to the density. So it's a very complex thing, but we're going to do more on this later. So we're not going to worry too much about it now. Let's just take a note about solids. So of course, we've really focused on fluids so far. We derived our wave equation in terms of fluids, and most of this course is concerned with sound propagating through the ocean, but of course it interacts with the seabed, which is a solid. Now let's go back to our definition of a fluid, which we never did. We just assumed we were looking at fluids. So let's look at what is the definition of a fluid. A fluid, by definition, deforms continuously under a shear force. Okay, and a solid, simply put, does not. So what do we mean by shear? Okay, let's, instead of drawing our parcel of fluid, let's draw a cube of matter. And so really what we've been talking about, these compressional waves, right, where the cube is deformed normal to these two interfaces, right? The force is normal to these interfaces. But what about forces which are parallel to the interface, for example? Just drawn two of them. Well, these normal forces give us compressional waves, and these parallel forces give us shear waves. Right, easy to imagine how you might have different manifestations of this. Wow, that's actually not bad. So you see, have some sort of shear disturbance in that cube, as opposed to just a compressional disturbance. Okay, it's pretty good. I'm pretty good with this thing, right? So, okay, that's just a little side note. We won't talk too much about acoustics and solids right now. Okay, I want to do another little side. Some of you, when we were looking at the velocity potential, were probably remembering lots of E&M theory. Okay, so let me write my favorite thing. Recall electricity and magnetism theory. We had the electric field is equal to spatial gradient of some scalar potential, right? So this looks exactly the same what we just had with our velocity field. And just to put some words to it, this is what we call the voltage, right? Dot, dot, dot. Voltage. So we got the electric field. And scalar potential is the voltage. And, this is homogeneous isotropic media. There's a few things in there. So I just bring this up because obviously there's tons of parallels between these two fields and the equations that govern them. So if you do have fond memories and good knowledge of E&M, you can bring all that stuff with you to this course, and it will be very, very useful. And it actually can be very useful to think about these problems analogously almost all the time. So, for example, what is resistance? We know what resistance is in electricity and magnetism, or impedance, right? Frequency-dependent resistance. So what does that look like in acoustics? What is acoustic resistance or impedance? Question mark. So the specific acoustic impedance is, we use Z. It's actually just the ratio of the pressure and the velocity. And so I think, that's sort of the intuitive definition. What we're talking about is, a material property that relates how pressure drives particles through the property, through the material or within the material. Okay, and just for clarity's sake here, I'm going to say that V here, so I've dropped the primes. We're not going to worry about primes anymore. And really here I'm talking about, I haven't put the arrow over the V. We're not talking about the velocity in terms of a field property. We're talking about the velocity in terms of, we're talking about the velocity in terms of its scalar magnitude. Okay? So sometimes, the absence of a symbol can be very meaningful. So, okay, that's a very nice little easy definition. Now, you'll also probably remember in electricity and magnetism, the Poynting vector. Yeah, I think I spelled that right. Yeah, okay. What about the Poynting vector? So what was the Poynting vector? It was the directional energy flux. Oops. So in the same way that, we have electromagnetic waves that are carrying some energy, we have acoustic waves that are carrying some energy. So let's see how far we can get at deriving something to describe that property. Okay, so we're going to go back to the linearized Euler equation. So that's conservation momentum equation. And this time we're going to take, we're going to dot it by the velocity. And I'm dropping the primes now. Okay, right? So that's the linearized Euler equation, and we've added the velocity out front. So what happens here? We have vector times the gradient of pressure. So we can use some nice identities. You got to use, anytime you got something like this, you got to use some identities. This one's just basically reverse chain rule, right? Or chain rule reorganized, right? And we have a relationship for that third term, right? Oops. Right, so we can substitute that third term as P times 1 over rho, d rho, dt. And here I've put the rho naught, but I haven't put the prime on the rho prime. So this, where did we get this from? This was from mass conservation. So we have this term here, and of course the left-hand side. So the left-hand side, 1, we can write as d by dt of 1/2 rho naught v squared. And 3, we can write as d by dt of 1/2 p squared over rho naught c squared. And there we've used our nice little relationship that rho is equal to p over c squared, rho prime, really. So we can rewrite this whole equation as d by dt 1/2 rho naught v squared plus 1/2 p squared rho naught over c squared plus del dot I equals 0, okay? Where we've defined I as P times V. And so, okay, some of these things are looking very familiar to you. I know you can't help it. You're thinking 1/2 rho V squared. Well, that is just kinetic energy, right? But, well, 1/2 mv squared would be kinetic energy, but here we have rho, so it's kinetic energy density, right? Okay, so this is your acoustic kinetic energy density. And similarly, this looks awfully familiar. Here you have a potential energy density. Okay. And what does it make this? Well, here we have the divergence of this product of pressure times velocity. So really what we have is an acoustic intensity. I mean, the symbol gives it away, or you can think of it as an energy flux, right? So you have this scalar field times this vector field. So you're talking about a flux. So this is the acoustic energy flux. And really, this whole thing, right, this whole equation, since it equals 0, is really a conservation of energy equation. Unsurprisingly, because think about the parts that we used to make it, right? Conservation of momentum and conservation of mass. And so that equation, this conservation of energy equation, now gives us a relationship between, pressure and energy, right? This is definitely an equation that's worth, whoa, don't have enough iCloud space. You guys ever get that message all the time? Okay, we got this energy, we know the relationship between energy and pressure, and, if we go back, we had relationship between, we looked at relationships between pressure and density, right? And we looked at relationships between pressure and velocity. So that's kind of answering some of our questions from lecture 1. Thanks for watching this one.